Okay, this is lesson 1 of the Cudmore List Cudmore series. First thing we're going to talk about when we talk about energy is the idea of work, power, and energy. So what are work and power, and how does that relate to energy? So, work is done whenever a force causes an object to move. So when we define work in physics, it's a little different than work normally. Work in physics is something really specific. It basically is only when you have an unbalanced force causing an object to have a displacement. So we calculate work from the formula. Work is force times displacement, W equals Fd, where W is the work, and the unit for work is joules. F is the force, which, as usual, is in newtons. Now, one really important thing to keep in mind with that equation, since work is force times displacement, if you apply a force without having a displacement, there's no work done. I know this may sound kind of counterintuitive because you're used to the idea of basically doing work without there being a displacement, but in physics, work has a really specific meaning. I often like to say, basically, think of it as useful work or physical work. So, if you apply a force with no motion, there's no work done. If you're applying a force perpendicular to the motion, because force is a vector, there's actually no work done. So in both the cases of the diagram here, you're actually not doing what we call physical work. In the second one, you would be doing work if you lifted the box, causing a vertical displacement, but carrying it straight off, no, there's no actual physical work done. So, a good example is, a typical question, how much work is done by a boy pushing a car with a force of 800 newtons for a distance of 200 meters? Again, you'll notice, mass of the car doesn't matter, nothing. All that matters is how much force are you applying, what's the net force, and what's the displacement. So, once you've done that, the math's actually pretty easy. Work is force times displacement, 800 newtons times 200 meters, so you get 1.6 times 10 to the 5 joules, the joule being the unit of work. By the way, anytime we have a question with energy, work, it's going to be joules. That's going to be your unit. Okay, since direction is a vector, only displacement in the same direction as the force creates work. So for example, in this case that I'm showing here, only the horizontal component, only that actually has any effect at all on how much work's done. We don't really care about the vertical component at all. It doesn't really matter. So the equation is basically the same equation, except it's just using the horizontal component, the component in the same direction as the work. So its work is Fd times the cosine of the angle theta. So if you've got an angle, it's Fd cos theta. W is the work in joules, F is the force in newtons, D is the displacement, and theta is the angle between them. So basically it's what gives us the component of the force in the direction that we're actually moving. By the way, if I give you an equation in this unit, or sorry, an equation, if I give you an angle, you're going to be using this equation. It's the only reason I would actually give you an angle. If I don't give you an angle, assume the force is in the same direction. You can use the one that we just did. For this one, again, it's not really that hard. If you're pulling the wagon now with a force of 55 newtons east, 45 degrees north, for 85 meters east, you would just say, work is Fd cos theta. So it's 55 times 85 times the cos of 45, and you get 3.3 times 10 to the third joules. By the way, you'll notice there's no direction on that. Work is a scalar. Work and energy are how much. There's no directional component to them at all. All right. The other unit we use when we talk about energy being transferred is something called power. And power is simply just how fast is the work being done? What's the rate at which the work's being done? So you find power just by dividing the work by the time in seconds. And that gives you a term power, which you've seen the unit before, that's watts. So if you remember all the way back to grade 9 with electric power electric power was just how much energy is used every second. Basically, it's just a special case of this. So once you found the work, divide it by the time, that tells you the power. All right, example. So let's put it all together. A person lifts a 50 kilogram box 3 meters in 34 seconds. What power was developed? Well, if you're lifting something, you got to be applying a force equal to the force of gravity. So that'd be 50 times 9.81, so 490 joules. The work is the force times the displacement. The force is all up if you're lifting it. The displacement is also going to be up, which means we don't need to worry about an angle or anything like that. You go 490 times 3, that gives you 1470 or 1.5 times 10 to the third joules. To find the power, you divide the work by the time. If we lift it in 34 seconds, you end up with 44 watts. So that's what 44 watts basically means, is you are doing a certain amount of work in a certain amount of time. It's how fast are you doing the work. All right, now that we've talked about work, we can get to energy. Now, what energy actually is something kind of weird. It's a measure of work. So energy is a measure of how much work is done on or by an object. So it's how much energy an object gains or loses. So work, we could also write as the change in energy, delta E. Don't forget, delta basically means final minus initial, so E2 minus E1. So for example, if you've done 20 joules of work in one of these questions, you require 20 joules of energy to do that work. So that's all energy and work really are, is work, they're a way to keep score of what you've done. So work is force times displacement. Change in energy is just the work. So we can use work to figure out energy, we can use energy to figure out work. Now that's really important because there's actually no way in science to measure energy, how much energy something has. You can only measure a change in energy by measuring how much work was done by the object or on the object. So, the last thing we need to talk about is this concept of positive and negative work. Now remember I said, work can be done on something to increase its energy, or work can be done on something to lose energy. So, positive work means when you subtract E2 minus E1, you get more energy at the end than you had before. Okay? So, you've gained energy, the object has gained energy. We call that positive work, or work done on an object. Okay? So work done is positive if it's work done on the object. If E2 is less than E1, we say that's negative work, so you've lost energy, and we say that's work done by an object. So work done on an object increases its energy, work done by an object decreases its energy. So one is positive work and one is negative work. All right, that's it. Head on to the worksheet.